So hey everyone, I'm Ahmed, and I'm a cloud consultant at a company called CCL, and I'm also an MVP. I do blog and put stuff on social media, YouTube, and uh, Twitter and LinkedIn. And today I will be talking about some of the basic concepts that actually bugged me when I'm trying to understand generative AI. And a lot of the terminology that I will be talking about today is I will only talk about how do you understand it, not talking about anything mathematical. Not going to go into the deep details of like the science behind it, but I feel that it is actually stopping a lot of us when we try to understand what is this new LLM or generative AI. And I'm already starting to use some terminology. So, but when you abstract it to the basic, it is actually quite easy to understand what is it that we are trying to solve and how did it actually, in a way, how did we teach the machine to actually think? So the first thing that I want to talk about is that the idea of LLM. So LLM stands for large language model. And the idea is that computers actually do not understand characters. They do understand numbers. So the first thing that if you want to teach a computer to think and talk, I will not say, to actually understand your text and give you text back is to convert those numbers into characters into numbers. So for the sake of an example, let's say that you've got like the English dictionary, and then you start with giving each word a number. So like you start from A to Z, and then say like the first of course, this may be not the first letter, not the first word in the English dictionary, but for example, say it is the first one. So you say, okay, so about, you give it 1, above you give it 2, across 3, and so on and so forth, till you reach the end of the dictionary, and then you give the word zebra 600,000 or whatever, right? So this way, this is an understanding that we first came up with, which is like turn the characters, turn words into numbers, and then start with using all the beauty of math with statistics and probability. And then you, whatever mathematical equations you were able to run on numbers, you will be able to now run on words and characters. So for example, the word, hey, how are you, could be turned into 5, 25, 30, whatever. Of course, numbers will be so much high up, but for the sake of example, we'll use like small numbers. So basically, you started to represent your words and characters with numbers. So what goes behind the scene is that actually, instead of numbers, one other concept in when we are jumping into the world of Gen AI or LLMs is the idea of a token. And for example, you hear that ChatGPT has got like 128 or 200K token size, and then more and more each new model are saying like the context window or the number of tokens that the generative AI could actually take is increasing. So if you, for example, if you jump into this website, which is ticktokenizer.vercel.app, and you'll get this window, whatever you put in this window, it will turn to numbers. And the idea is that each color here, the large language model actually, and the algorithm that tokenize your text actually turn into a number. So for example, this word like lim underscore start, it turns it to 100,264. And then after that, the word system is 9,125, and so on and so forth. The idea is that we are trying to use math and trying to use what a computer actually understands. So we turn those words into tokens. And as you see, sometimes the token is not just one word. So for example, in here I said like hello Ottawa Azure. The space before the A and the character A is one token. Then you have the OT as one other token, EAR, and so on and so forth. So there is some algorithm that goes behind this and then tokenizes your words and characters. it is like the more algorithm, new versions of an algorithm, the more it becomes smart in tokenizing your characters and even your code. So the first step is to teach your computer is first tokenize your characters and then turn it into numbers, use those numbers, and then start to use whatever math that we already have. Okay, so now basically what is the LLM do, or like how does it actually work? So the LLM work by predicting one word at a time. So for example, say that you give an LLM the word R and they say, can you predict the next word? And because the LLM has been trained on the whole internet data, it actually has some statistics of saying like, okay, in the whole of the internet, I have found the word R, or maybe the number 5, and again, when we are just simplifying the representation of the characters, I have seen the number 5 and 75, which is RU, 5% of the time. And that is out of 100. And then I have seen are they, which is, for example, if a sentence is like, how are they? You would say it is 5% of the time. And then are things, another 5%, are fine, and so on and so forth. So out of a big set of data, which is the whole internet, the LLM has actually, we have given the LLM all this data, and then turn this data into numbers, and then using statistics and probability, the LLM has actually found out that if you have only 2 words, which is called 2-gram, if you only have 2 words, and you have set of those 2 words, it has seen the RU 5% of the time. So if you are asking the LLM, can you predict what is the next word that comes after the word R? It would either give you RU, are they, are things. It depends on like what is the statistics, but how accurate is it? Is it the thing that you want? It will not. It will be a hit and miss because you are just giving it one word, and then you're asking it to, can you complete this word? Okay. If we take it a step further and then say like, we give it now 2 words, and the context now is 2 words, and we are saying like, can you predict the next word? So the context window is only 2, but as you could see here, the probability is so much different now, because if you just say like, how are, with the word you has happened 50% of the time, because now it is like much more accurate because it knows more than what is it that you're trying to say. So instead of just saying are before, which was like, are you, are they, and 5%, I don't know. But now the word how are you is like, oh yeah, I've seen this one half of the time. Each time I see the word how are, there's very high possibility, 50%, that it is actually you. And there is also 30% here, for example, they, you could say like, how are they doing, right? So it has seen this combination, how are they, 30% of the time. But again, it's still hit and miss. It is very low probability that is like to say the word how are animals. It might have found it in the context of its training data, but it's really low, so it's not going to go and predict the next word to be how are animals. And then we take it another step further. Now we say, hey, how are you? Sorry. And then ask it to predict the next word. And now the you is really high, but the they, which was 30% before that, it's now 5% because you don't say in the internet, hey, how are they, right? You would say, hey, how are things, which is now increased 10%. So as you could see here, the more context you give the LLM, the more accurate it is to predict what is the next word and what is it that you're trying to do. So for example, if you give the LLM, which is the ChatGPT level, sometimes if you give it the context of 1,000 words, 100,000 words, right? It would actually very accurately predict what is the next word, even if the next word could be something really unlikely. So because of the context, so like let's say, for example, you are talking about mountains, or there's a story about cars, and then you give the context, the idea of the LLM. The idea is saying that, hey, and then she goes to, and then you give it a space, and then the actual word is she goes to the moon, and it's like, goes to the moon? Why would she go to the moon? But if you go and read the whole context, it's all about the space, and she's like planning to go there, and then taking all that time, and then final word, and then she goes to the moon. So so if you look at it now, I might be giving you the idea is that the LLM is just statistics, and it's just probability. It's just predicting what is the next word. So why is it that we've only came up with it very recently, and why didn't we just use that before? So the reason is that if you take this idea of like 1 gram, 2 gram, and 4, and so on, if you take it more and more, it becomes really computationally and memory intensive to actually build that on a computer. Because, so let's say that we are talking about, we just said that the English dictionary is 600,000 words, right? So if you say that our vocabulary is 10,000, okay? It's not 600, just 10,000 words. And then you put that in an Excel sheet, and then you say, okay, so I'll put a word out of all these 10,000 in each row. And then in front of that word, I'll put another, in each column, I'll put one word of all these 10,000 words. So your Excel sheet is 10,000 by 10,000, because these are all the probabilities, right? So now you've got this, what is it, 100 million cells of an Excel sheet. That's a lot, right? And we're only talking about 2 words. If you add another word, that is another 10,000 by 100 million, so you're almost reaching a trillion word. So you could see how we are, if you go here, it becomes really computationally difficult and memory intensive as well, because if you add more and more words, it becomes really hard for the computer, and when you store it, to actually predict what's the next word. So for example, we had autocomplete within programming, we had autocomplete on our iPhones. It is all good. It's not using LLMs, which is what this is all about. But what we couldn't do is that we couldn't do it on the context of, like, say, okay, so you give it a sentence that is like, say, 100 words, and they say, can you predict what is the next word? It would have you would have, in theory, it's so easy, but in practical, it's really hard. You can't actually build it on a practical computer. So in 2017, a paper came out, and it was called Attention is All You Need. The idea is that this is a transformer, which is the T in the GPT. You don't need to understand what is this, and it is mathematically a bit difficult. But all you need to do is all you need to understand, which is something I'll tell you about, is that there is a very interesting trick that the transformer is doing, is that it is teaching the LLM to actually give weights to words. So not every word gets the same weight. I'll explain that in a second. So say that you have this sentence, right? So like, my dog's name is Ben. He's a big dog. Ben likes to play fetch with me, right? So you give this sentence to the LLM with the using of a transformer, right? So this is a long sentence, and we are in here on the word play, and we are asking the LLM to say, like, can you predict the next word, right? So what the LLM is doing is that with the transformer, it is giving weight to all these words, and it knows by training on a big context of data which word it should actually give weight to, which one is the most important word in here. So it knows in the first sentence that Ben and dog are the same. It knows that Ben is actually a dog. So in the next sentence, when you say Ben likes to play, he's not gonna want to play football because he's a dog. So the LLM is predicting that, okay, so Ben is a dog, and Ben would like to play what? So it would most likely say it would like to play fetch. So it will predict that the next most probable word to complete this sentence is the word fish, instead of it saying soccer or whatever. So all you need here, so this is actually the big breakthrough moment that came out in 2017, is that instead of giving every single word in here a context, and if instead, it's actually really good that it could infer what is the whole paragraph, sometimes even more, that it could infer what is it that you're trying to say, and then predicting that actually the most suitable next word should be something like fish. So that is where the big change happened. That is where everybody was like, oh, this is like a big breakthrough. And then people started to think that this is good. This is something that we could actually build on top of. Okay? Yeah.
Were you already doing that in grammar back in 2010, 2012?
You mean Grammarly or?
And grammar, so suggestions on grammar, for example, and what words to use, because I'm a wordy guy. I like to talk and present something, but I found out though that I talk way too much. And once I started using grammar properly for the word, then suddenly I realized that I needed to change how I spoke, and so I did.
Yeah. So
but
sorry.
This is almost, to me, it appears to be the same thing.
Yeah. So that's a very good question. The idea is that when you're talking about the grammar, it is so like I talked about it in a very simplistic way about autocomplete. So the rule is that if you give in the context of the word hey or like how are you, you would just be using like your statistic and saying. But with grammar, it is still using statistics and probability, but they're adding more and more rules. Say like, okay, so like it's not just a word after a word. This word needs to have some extra conditions and actions. So it is still using probability and statistics, but it doesn't understand the grammar. And when I say the LLM understand, it doesn't understand because what you'll see when I'll go through this is that it's all numbers and it's all correlation, but it gives you the indication as if it is actually understanding what you are saying. So like with the grammar, with using, for example, ChatGPT, you give it a sentence and it's like, why is this grammatically wrong? It would tell you why. That is different on a different level. This is what the attention is all you need. So it made it scalable, made it possible to actually come up with such answers. But there is a lot more that was built on top of this that make it gave us the ChatGPT 3, 3.5, and 4.
So when you're typing in Bing and you're going, how was the weather will come up without you even typing it. So is that?
Oh no, that's autocomplete. Also, like when you go to Bing and it's like,
not on the phone.
The autocomplete. Yeah, that's not LLM. Yeah, that's not using LLM. Yeah. So now I want to explain one concept which is I actually touched upon here, which is that when it starts to generate language, what it is actually doing, it is always predicting the next word. I talked about it briefly here. So for example, when you say like, how are you? And then you give it 3 dots, it says like there is a 60% likely that the word is I, because I'm like, how are you? I am fine. Or it says like, we are good, or thank you, something like that. It goes through probability, but then the next word, again, it's like, okay, how are you? And then I. And then now the most likely word is different. It is the word am. And it goes on and on until it goes into the level where it says, I am fine. So where I'm going with this is that if the LLM is really predictable, so if the LLM is like each time you ask it, like, how are you? I am fine. Like if you ask it to complete it and it's always giving you, how are you? I am fine. That's not so interesting. That's not so creative. So like if you ask right now, if you go to ChatGPT and ask it a question, and then ask it later on the same question, it will give you a different answer each time. It's not the same answer, and there is something that goes behind the scene that is causing this what we call a creativity, or like it's not giving me the same answer every single time. So the problem that the transporter model actually solved is that made it computationally possible to actually build on top of this. But then we started to add more and more intelligence to it, so until it became what is it right now. So I want to now talk about the idea, which is the temperature. So the temperature here, we are talking about. We just said that if we ask the LLM to say how are, and then it says like my most likely answer is you. So how do we make sure that it doesn't give me the same answer each time, and otherwise it will become really boring. So we came up with a concept called the temperature. So the temperature is between 0 and 1, with 0 being completely predictable, always giving you the same answer. So like if you say, give me the 10 most common name in New Zealand, it would, if you have it on 0, it will always give you the same answer, no matter how many times you ask it. But if you raise the temperature all the way high to number 1 and then say what are the most common names in New Zealand, it would start to give you names from all over the world, because that's what we call it. It is start to hallucinate, because the creativity temperature here is really high. It start to go and then say, instead of saying how are you, it says like, why don't we say how are they, or how are things? And that's where it becomes creative. That's where we get the surprise of saying the word. And I was like, oh, it is actually creative. That is one of the things. For example, if you ask ChatGPT to give you a poem, it would go and give you a poem that's literally never been created before, because of this calibration of temperature, that it is not giving you the same answer that it's seen on its training data. So as I said, the more high the temperature, the more it starts to give unreasonable things like how are animals, because you are increasing the temperature, and it starts to hallucinate. Okay, so we are halfway through. Now, so like we are in a place, and this is from OpenAI blog, when they released ChatGPT, or GPT, I should say, 3.5. So you don't need to go like you don't need to like focus a lot on what is the supervised fine-tuning. Sorry, the idea is that. So we created this model that is actually really good in completing the next word, right? So like the model you would give the model a sentence, and it would say, okay, this is the next word. Give it a longer sentence. Keep on doing that until it gives you the end of the sentence. But the problem with that is that this is not so useful. It is, you could call it autocomplete on steroid. It is really good in predicting what's the next word, but you get no value out of it. What you want, which is the ChatGPT experience, where you want to ask it a question and then it gives you an answer. So when we finish training the LLM on all the data on the internet, and then the base model, it knows everything on the internet, it's got a lot of data. You wanted to say, for example, you wanted to give you an answer to questions. So what we did is that we asked a bunch of people to create, say, 1,000, 10,000 document of a question and an answer, and then you give it to the model, and then say you train it a little bit. It's not going to forget whatever it trained already on, but you just train it on this new piece of data, just fine-tuning. And I know Daniel, yes, all people asking is that, can I fine-tune it on my model, on my data? Sorry. Yeah. So like you give it this question and answer, and then it starts to learn not a new information. It starts to learn a new behavior. So it knows that each time there is a sentence that translates to numbers and then understand that this is a question, there's always something that comes after that, which is the answer. So you give it more and more questions and answers, and I was like, oh, I get it. I get this. When I see a question, next time I'll give you an answer. So what happens here is now all of a sudden, the autocomplete on steroid, or like the LLM, which is really good in predicting what is the next word, it now became useful, because now you could ask it, what is the size of the earth, or like who's the president of whatever, it would give you an answer because it learned when it sees this behavior of a question that there is an answer that needs to follow. So that's all good. And now the model is really good in giving you like an answer to a question. The issue is what happens if the model gives you an answer that you don't want? So if someone's saying like, how can I create a poison or whatever? You don't want the model to actually just say like, oh yeah, of course, this is how we do it, because it knows that after a question, there should be an answer. It doesn't have a value. It doesn't have good or bad. It doesn't know dangerous. It doesn't know things that it should not do. That's when and I keep on saying we, that's when people at the OpenAI and other organizations came up with the idea of reinforcement learning with human feedback. So the idea is that you give a bunch of people, 1,000 or more, access to this model, and then say like, you would ask it a question, and then it would answer. And then if the answer is a good answer, or if the answer is like, how do you create a poison, and then it would give you the answer, you would say, you tell it, like give a feedback to the model saying like, bad model, that's not good, don't do that. And it would have a punishment and a reward function built into it. So, and the model is just looking for the reward. The model is like desperately trying to get this is something programmed into it. So it needs to get the score high. It needs to be rewarded, right? So yes, exactly. So you ask it the question again. I was like, how do you create a poison? I was like, sorry, I'm a large language model. I can't answer this question. So the question is here, why was everyone surprised? Why was this big jump when we came up with, when the ChatGPT, I think was a year ago, 2 years ago? Yeah, something like that. When it was released to the world, everybody was surprised. It's because of three things. The first thing, which was the scale and speed. So with more, this is something that scientists realized, and people working on the LLM, is that with more scale, with more access to compute and memory, and the underlying infrastructure being more powerful, the model started to internalize a lot of concepts that we didn't know that it actually could internalize. So it would internalize the idea of a question or an answer, the behavior of, if you get a question, you need to have an answer. So that was something that came out of scale. The other thing, which is the simple idea, again, it's simple in theory, the idea of temperature. So like this idea unlocked the idea of creativity, which was also surprising because a lot of people thought that if you came up with the idea of whatever artificial intelligence, creativity would be the last thing that the AI would actually unlock. But with this simple idea, we unlock the idea of creativity, just increase the temperature and it will give you a surprising answer. And then finally, the idea of steering the model with, so fine-tuning the model with data that you wanted to give an answer for, and again with the idea of reinforcement human feedback, reinforcement learning human feedback. So how am I doing on time? It's like half an hour already. Should I keep on? Okay, good. Good. So now we come up to another concept, which is also something that actually helped us unlock the idea of, I just found a typo, unlock the idea of like the language being able to search in a very big amount of data and then coming up with answers so quickly, which is the idea of a vector database. So this is from this blog, and the idea is that if you have masculinity and femininity and then royalty, each in a, like if you have a world that only have 3 domains, right? You have royalty, masculinity, and then femininity. And then you have the word king. And then you put the word king on a scale, and then you measure this word and compare it to this domain, each domain, right? So before I go into the details, what are we trying to do with this vector database? We are trying to teach the model, or like we are trying to teach the computer, I should say, the idea of meaning. So instead of it just knowing that, so like I just said that, for example, it knows that Ben and a dog, they are the same because it's because of intention. It's the idea is that we want to train the computer to actually make inference and make correlation between things that might sound or like on a scale of data might sound different, but when it starts to realize that they are the same, it would figure out, oh, actually king is related to queen and to a woman and to a princess. So how did we do that? So the idea is that we said, okay, for a king, royalty it's 99%, masculinity it's 99%, and femininity is 0.05. And the reason that these are like not 100 and zeros because in statistics doesn't work this way. You always have to have a room for error. And then you go again, the queen is 99%, masculinity is 0.05, and then femininity 93, and then so on and so forth. So now you translated on this world with 3 domain, you translated things like king, queen, women, and princess into numbers, into things that the computer could actually understand. So, and then you add another layer. So for example, in here, we've got the king, and then we've got the man. So like how much is the possibility for a man to be a king or a royalty? That is really low. How many people in the population are actually kings is very low. Masculinity is the same and femininity is the same. But what's really interesting is that we could now, because we turned those characters, those words into meanings, and the meaning of it into numbers, sorry, we can now start to do mathematical equation on them. So if we say, okay, so we've got the king and the man, if we multiply the value of the numbers that we associated with the word king from the value of the number we associated with the word man, we get something else, which is if 0.99 minus 0.01, it's 98. 99 minus 99, it's 0. 0.05 minus 0.05 is 0. So this is 0, and this is 0, and this is 98%. So you get the idea that if you take the man out of the king, you are only left with the idea of royalty. Okay? So we take it a step further, and then now say like, okay, we've got royalty, let's add in the values for a woman, and you get where I'm going with this, which is 0.98 plus 0.02, 0 plus 0.1, 0.999, you end up with a queen. So we took the meaning of the word king, we took the man out of that word, we ended up with royalty, added the woman, ended up with a queen. So this way, what happened is you could actually represent everything in the world with numbers, and those numbers could be on a vector. So for example, you've got the word king and a man, queen and a woman. If you take the word king and abstract man from it, you get the word queen if you add the woman to it. So with this abstraction level, we are now teaching the model to even infer what those words are. It's not just going through the database and saying like, okay, I found that R and U actually come together a lot of the time, and R and phi. It's actually going even a step further, because it now start to infer things that is surprising to us, because we taught the computer what is the meaning out of associated with each of those words. And if we take this one a step further, the computer, the LLM, start to actually connect stuff that are very surprising, but also for us human is very intuitive, and it's not very surprising. So like the lion is the king of the jungle, tiger hunts in the forest. It knows that these guys are actually close to each other, because you could subtract and multiply and get from a lion to a tiger, jungle to a forest. These are together, but this one is far away because it doesn't have anything similar or related. And the vector actually doesn't just relate one word to another. It actually could actually relate whole concept, like thousands and thousands of words with one with another. So like when you ask a ChatGPT, or like I keep on saying ChatGPT, but when you ask the LLM, it would actually give you a lot of answer that is very thoughtful. It was like, oh, it actually brought all these ideas together. It's because we are giving it those skills, and because we are using things like the vector database. And that's when, like right now, it's very popular for startup to actually work on building a new vector database, or like building on top of a vector database. So, okay, so now we understand in a way how did we come up with the idea of the autocomplete. Then we had the idea of the transformer, and then we came up with a supervised fine-tuning. I forgot the word. Yeah. Yeah. So reinforcement learning, human feedback, and so on and so forth, until we came up to the idea of a vector. So now we are in a place where the ChatGPT is now having all these tokens, all these ideas. You could ask it questions, you could ask it all sort of interesting stuff, and you could come up with very creative and then very logical and understandable type of answers. The final topic that I'll talk about, and I promise this is the last one, which is the idea of a neural network. This is a very nice diagram that I found on the internet. So so we have talked about all this beauty that the ChatGPT is doing with text, but now you could see that a lot of LLM can actually understand images, could actually generate images, could actually understand text and images, and so on and so forth. So what I'm trying to do here is, like in a very like high level, just give you the idea of how did we came up with the idea of turning an image into a text, and then and text to an image. So this is the human neuron, and then basically this is a cell. You've got the dendrite for the input, and then you've got the axon for the output. And what this is that it is like we try to replicate this human cell and build it into an artificial wall. So we've got this circuit, and then we've got input for this circuit, and then an output. So what this circuit has, it has so let's say, for example, a human eye sees a line, okay? So the start of the line, it is getting input, and then it goes through, and while you're looking at the line, and then you are getting more and more feedback, and then until there is a threshold within this neuron that actually get triggered, and I was like, oh, I know what I'm looking at. That's a line. So what this is trying to replicate is a very similar idea. So you get A1 as an input, A2, A3, which are in the digital world, could be pixels or of a camera. And then these inputs all go into this cell, and then they add up more and more until the cell reaches a threshold that I was like, oh, actually, I know what I'm looking at. I'm looking at a line. So we, in a way, replicated what the human brain is doing. We built that into into computers, using a logical circuit, and then some input, and then it would give me an output if it reaches this threshold. So, and of course, because the world is full of cats, what this is doing is that, so each one of those nodes is actually looking at a piece of the image. So let's say that the first one is actually looking at the ears, right? So the first one says, start to look at the start of the ear with A1, A2, A3, and it says like, oh, I think these are ears. And then the next one again. So the first one says like, oh, I know what I'm looking at. I'm looking at ears. The next circuit will say like, okay, I'm looking at the eyes. The next says like, I'm looking at the body. And of course, this is just 3, but in reality, it's like a lot much more bigger. And then it sees that it finds a tail. So it goes through deeper, and that's why it's called like deep neural network. It goes into the next level, and then this level is looking for the input from this circuit, and this one is saying like, I see ears, and I see eyes, and I see a body. This one says like, I see a tail. So this level says like, oh, I think I know what I'm looking at. It's an animal. It still doesn't know what is it until it reaches the final level. The final level with all of these inputs, it is actually looking at all this input, and it's like, that's not any animal. because of the shape of the ears and the shape of the face, that's actually a cat. So we turn a very abstract idea, which is like an image with multiple pixels, into a trained model that it would actually go through these circuits, and then it would say like, oh, I know what I'm looking at. It's a photo of a cat. So to take this even a step further, I explained this just to tell you the idea of what is the diffusion model, which is something that helps us turn text into images, turn text into like a video or audio, depends. So the concept here is that this is the idea of a compressor. So like normally this is, you give it, for example, say this word, a cat jumping out of a window, and then you give this into an input. So what this algorithm is going to do is that it's going to try to compress this into this purple three blocks, but why we're trying to keep as much useful data out of the sentence. And we'll lose data because you're asking it to turn like 2, 3, 4, 5, almost 6 words into 3 words. So it's going to lose some of the data, but it's supposed to be trained very well that it would be able to keep the meaning out of this data. So you compress it into these 3 blocks, and then you tell the model, can you decompress it? Can you tell me what did I give you? And it goes and it's like, oh, a pet is leaving the house. It is in a way accurate. It is a pet and it's jumping out of the window. It is leaving the house, but it's not the word that you gave it. But that's not a problem because in a context, for example, of an image or a video, it is, our eyes are adapted. If you see a glitch in it, you still know what is it. So the idea is that when we say, for example, intelligence is compression, so what that means, there is a theory that says that if you understand a topic really well and someone comes your way and is like, can you explain it to me? And they will ask you, can you explain it to me in a very short and condensed idea? So if you really know the idea, that would be super easy for you to compress it because you know it all. So what someone says like, okay, so if we get the Wikipedia and we try to compress it on and on, there's even a competition that the more you compress the Wikipedia, someone is willing to pay some money. But the idea is that the model that would be able to compress the idea and then give it back again without any loss would definitely need to develop intelligence. So in a way, that is what the model is trying to do. So like, for example, ChatGPT does not save the whole internet data. It doesn't have access to all the internet data. It has an idea of what this internet data is. It would sometimes, if it sees the same data on and on, it would be able to say like, okay, this is what you're asking me. But if you ask it something, it's not gonna pick out of it data and give it back to you again. So now we come to the idea of the diffusion model. So what did we do is that we wanted to teach the model to actually detect images of cat with added, not actually detect, actually generate images of cats. So what did we do? We took the cat here, an image of a cat, and then we added a little bit of noise. And then we add this image with the noise. We give it to our model here, this one. So we give it to this model and then say, can you remove the noise from here? So like, this is just what the model is trying to do, right? It is, we give it the image, we add noise, and we ask it, can you remove the noise? What it would do, it would actually be able to give you back the image without the noise, because the noise, it would realize the values of these noise pixels that you added doesn't make sense in the picture, right? So it would detect that this is a face of a cat. And then you add even more noise, and it's like, can you detect the cat? Can you remove the noise, sorry. Does that again, bring it back to here. Until you end up with complete noise. And then it's like, can you remove the noise? I will try, it will give you this image. Yep.
It's just the opposite of adding a watermark to an image.
Yeah, yeah.
It's exactly the same. And if you actually squint your eyes, you can still see the cat.
Yes. Yeah, the model would be able to easily detect the noise because it knows that it doesn't make sense to be here. What is really interesting is that if you take this this neural network that you're trying to remove the noise, this neural network now developed the idea to look for cat faces. So if you take this this model that actually worked through removing the noise from this image, that you turn it to this and then turn it back to this one, each time you give it this noise, the model will be looking for cat faces, even if it doesn't exist. It is so eager to get reward, it would start to make up stuff to say like, oh, this is noise, but I know that I think it's a cat face. Let me actually tell you how. And it would actually start to generate a cat face. But the thing is, that's not the same cat face that we started with. That's a different face. So, and you do the same with the same model that was learned here, and then it will start to, if you give it a complete noise, it would take it all the way and then generate a cat face because it is looking for a cat face. It doesn't have to be the same face that it started with, but you now train the model to actually create an image of a cat out of noise. And again, this is, oh yeah. What is very interesting now, guys? Yeah. Sorry, let me just take it back one step. Yeah, so what we did now, for the same model that we used to actually train it on the cat faces, we added this text, which is a cat staring at me, okay? And then we took this one, we took this image, we added the text of a cat staring at me, and then we did the same, added noise and asked the model to remove the noise. But each time it's doing that, it's not just learning that it is removing the noise out of the image, it is also associating that with the word a cat is staring at me. And you do that the same, you add the a cat is staring at me, and then you give it, add more noise, ask the model to remove the noise. It does that, but again, with the association that this image is actually a cat staring at me. And again, until you reach the full noise, it is at this phase, it is with complete noise, but it's still not that this noise is actually a cat standing at me. So now what we have is a model that we started with training it on adding noise, then asking it to remove this noise, and then out of noise it would generate images. But because we added the context of text, what we ended up with is a model. You would say, can you create an image of a cat staring at me? And it would immediately know. It would take it all the way through and then generate the image of a cat for you. So that's all I had for today. And yeah, thank you. Do you have any questions? Yep.
When you say that we ask a question according to that model being trained, right?
Mm-hmm.
Apply any model into the organization, different users are tuning on that model. So how that context gets set? That model training will be according to behavior of different users, right?
So the model that actually you are using, you can't fine tune it. So the model you're using now, it doesn't train. So when you fine tune it, you have access to the model, and then you give it this small little bit of data, and then you ask it, go train on this data, and then it comes back to you. The model that, for example, when you use the model right now, this is this is something called like retrieval augmented generation, where you have a set of data. You tell the model, I'm going to ask you a question about where did Ahmed park his car, right? And it has this data in a database. It doesn't know the answer to this, but it knows that it knows what a car is, knows what Ahmed is, and then it goes and then says, like, okay, I don't have this data, but maybe it is provided to me. So it goes to this data that you give it for your company data, goes through it, and I was like, okay, I know because it goes. This data says like where did Ahmed normally park his car? Comes back to you. It doesn't need to be trained on what is the meaning of the word Ahmed or the meaning of the word car, but it goes through your data and then find the answer that it doesn't have in its data. So yeah, to answer your question, when you talk to a model, you can't fine tune it by the questions of people unless you are given that possibility. All right. Thank you, everyone. And yeah, have a good afternoon.